Welcome to this 12th lecture. In earlier lecture we have seen various power definitions, power gain definitions, and we have related the various powers at various points in the microwave amplifier network. Now also we have introduced these three power gains. Now is the time to find the expressions for that power gains. So G, we know that G is equal to PL by P in, and if we put those expressions that we derived, then we can write it as S21 square 1 minus gamma L square by 1 minus gamma in square 1 minus S22 gamma L square. So you see that power gain, it depends on the load, as we already said that it is independent of the source. That is why you see the source reflection coefficient gamma S does not come here. It is S parameter of the active device and various load conditions. Also from the network, if we look, that means just after ZS, if we look this Z gamma in, that will be also independent of ZS. That is why in the expression also we get this. Similarly, we can find out what is the available power gain, that we know is P AVN by P AVS. So it will be independent of ZL or gamma L. So this is again S21 square 1 minus gamma S square divided by 1 minus gamma out square into 1 minus S11 gamma S square. You see the similarity that gamma L is changed to gamma S, gamma in to gamma out, S22 to S11, gamma L to this, and from already derived ones we can now write the transducer power gain, that will be S21 square as said. You see this transducer power gain is dependent on both load and source impedance. That is why it depends on both gamma S and gamma L, gamma in, everything is included here. Now you see that sometimes this is the maximum gain possible, but for this we require, so GT, this is the maximum gain possible for a particular gamma L, gamma S, which is conjugately matched with the input and output impedances. This is the maximum that we can achieve, and so please remember that this is for conjugate matching input and output side both. But always we do not do such stringent ones, because always we need to know the loading conditions, source impedance and load impedance, to do this conjugate matching. Sometimes instead a easier one is done, that is just simple matching. This we can say simple matching. That means what we do, that we choose that Zs is simple equal to Z0 and Zl is also simple equal to Z0. You see, Z0 is generally a real quantity, so Zs and Zl we choose real instead of that complex thing. Actual for conjugate matching we require that Zs should be chosen as Z in star, Zl should be chosen as Z out star, but simple matching is this. But if you look at the expression of gamma s and gamma l that we have done, so if I have Zs is equal to Z0, gamma s will become 0 reflection coefficient, there won't be any reflection in the source, there won't be any reflection in the load, but that does not ensure maximum power transfer, that ensures that less than maximum power transfer. But sometimes we do that reflection, we just need to cut, we are not so bothered about maximum power transfer. So in this case this implies gamma s is equal to gamma l is equal to 0, and then what happens to this, you can say Gt simple matching, this will be what is the expression just now we have done. So here if you see, if I put gamma s and gamma l 0, it becomes simply S21 square. So by simple matching what we can achieve, whatever the transistor is giving me, whatever as a device it is giving me, I can achieve that. So let us see this first graph. Yes. So you see that here I am not taking advantage of this graph. So I am not a good RF engineer, but if this is sufficient that okay, whatever device transistor is giving, I want transducer gain to be that, I can do that simply by simple matching. Another important case is called, in many practical transistors, microwave transistors, we have unilateral amplifier. What is meaning of, obviously in an amplifier the S21, please remember that in a two port network S21 means whatever I am giving here, how much is coming here. So this by this is the S21. What is S12? That if something is reflected, how much is coming here. In many of the practical amplifiers, this S2 value is very small, practically I can call it 0. Sometimes it is not exactly 0, but very small. Compared to S21 it is quite small. So if we consider it to be 0, so in that case let us look at our this expression. You see that from signal flow graph I said that you can find out this gamma in is S11 plus this. Now here if S12 becomes 0, then even though you don't have a matching at the output, gamma in becomes practically S11. Similarly, if you write the expression for gamma out, that will be S22. So under this case we get that gamma in is S11, and then this transducer gain for unilateral case will turn out to be S21 square to 1 minus gamma S square into 1 minus gamma L square by 1 minus S11 gamma S square 1 minus S22 gamma L square. How it is different from a transducer power gain for a non-unilateral, that means in general one, you see the GT expression here, there is the presence of this input reflection coefficient and output load reflection coefficient. These two, sorry, this input reflection coefficient, Now, here that is absent. That means input reflection coefficient means I need to know what is the loading. Here it is independent and it can be much simpler design can be attempted through this. So, this is another special case that we will see in the gain definitions, that for unilateral amplifiers this simplification can be made. Now, let us generalize that now we are in a position to simplify our whole microwave transistor design. I can say that instead of this design, instead of, please look at these two figures, where is the transducer power gain, the 3 power gains, this. So, this was my actual circuit and this is the transducer power gain in the most generalized sense. Now, here you see that this is a total design, that means I need to find out gamma S, gamma in, etc. But now this whole thing I can attempt like this, that I have a source Vs here, I have an input matching network. So, basically I have a ZS, but with a input matching, here we will have an input matching network. This will be based on conjugate matching, and then I can say that with this input matching network, the job of it is to bring this to an impedance level Z0, and then let us call this, or that I will do later. Now, then I have the transistor S, and then I have this. There also will be an output matching network, and then due to this output matching network, instead of ZL I will say that I will terminate by Z0, and so here I will have that gamma S, here I will have the gamma in, here I will have that gamma out, and here I will have that gamma L. So, these two are equivalent things. Here I had ZS, ZL, etc., but that with input matching network and output matching network I can do it. And if we look here, I will say that this part will give me a gain of G0, this part will give me a gain of source side gain from this input matching network, and this side I will get a GL load side input matching network, and I will say my total GT is nothing but GS, G0, GL. As you see that I have various products. So, if we group it together, can I now say that what is GS? GS is equal to 1 minus, you see, this by this, because source is coming here only. So, 1 minus gamma S square, source impedance, source matching, they are coming here only. GS, I will have a GL is equal to 1 minus gamma L square by 1 minus S22 gamma L square, and the active part is G0 is S21 square. So, you see that a simple matching, people we have already found that simple matching, GT simple matching is S21 square. But if I do conjugate matching, actually I have 3 parts. So this is like simple matching, but I have 2 more degrees of freedom here. One is the input source matching, another is the output side matching. So by this, if I can design proper these 2 networks, I can get these additional gains, because here due to conjugate matching I will make maximum power transfer, and by that I can increase the gain. So basically, you see, when a transistor you have already chosen, okay, obviously while choosing we will choose a transistor which will suit our purpose, our impedance level, etc., and we will try to maximize this. But once it is chosen, there is not much role for a designer to play, but his role is basically to design here. That means if I want to have a high gain, I need to play with these 2 basically. So microwave amplifier design is playing with this input matching network and output matching network, so that GS and GL can be made higher and higher. Obviously there is interconnection between them, so independently these 2 cannot be done, but we will do something, we will see the techniques by which this can be done. But there is another problem here, that when I am trying to make this gain maximize, I should also understand that I am playing with an active device. So for certain loading conditions, because input matching network, output matching network design means I will have to choose properly my ZS and ZL levels, but to do that sometimes the whole active device become unstable. What is instability? That for finite input it is giving infinite output. We know that that condition is basically it can start oscillating, etc. I do not want an amplifier to oscillate, because that will start generating newer frequencies and also its levels, etc., that will start going up. So that we do not want from an amplifier. So we want to do a stability check for that. Now what is so the next part, before designing this, finally we will design these 2, that will be our basic main aim, but before that we want to do a stability check for a particular load and source condition. We want to see that what is the stability of the amplifier, because many times it happens in students project that suppose you are asked to design an amplifier, you see that finally you have loaded it such that it becomes an oscillator. So that means you have not given proper attention to stability. So if we do that stability check, so what is the stability criteria? That basically the Zin, if we see this, that this input impedance Zin, and also from this side I have output impedance Z out. Now Zin, if it has a negative real part, that means instead of resistive, if it has a negative resistance, also if Z out has a negative real part, obviously it is having an imaginary part plus imaginary part, which is the reactive part, but if either Z in or Z out or both they have negative real part, then I will start getting oscillation. It is obvious, because then whatever I am giving, suppose if Z in is more than it has a negative real part, whatever signal I am giving, the signal will start building up and then it will be start oscillating. Similarly in the Z out, that whatever reflection coming, that will start picking up and the device will start oscillating. So if Z in is having a negative real part, I can say basically that time the gamma in, because what is Z in we know, or what is the relation between gamma in and Z in? Gamma in is Z in minus Z naught by gamma out by Z in plus Z naught. So Z in, if it has a negative real part, then I know that gamma in is greater than 1. This you know from your Smith chart knowledge also, that in Smith chart every point that represents either an impedance or a corresponding reflection coefficient. Now, if Z in, you know, in the normal Smith chart that we use, they are the all we consider as passive impedances. So, there the real part is never negative, real part of any impedance is never negative, it is 0 to infinity, any value it goes. So, what is the, when Z in have a negative real part, basically the point goes out of our normal unit circle Smith chart, and that time gamma in becomes 1. Similarly, Z out is here, gamma out, its magnitude, that will be 1, because I know in the Smith chart, the suppose this is the point. So, this is the magnitude of gamma. Now, if that generally this radius is 1. So, if gamma in greater than 1 means this point, instead of here it is going here, or here it is going here like this. So, that means it is going out of the passive Smith chart of unit circle. So, what is the stability check? We can check these conditions, that gamma in, if gamma in is greater than 1, magnitude of gamma in is greater than 1 for certain or for any ZL and ZS combination, then we say that device is potentially unstable, or I should say, or gamma out is greater than 1. So, gamma in greater than 1 or gamma out greater than 1 for any choice of ZL, any particular combination of ZL ZS, then we say that the device is potentially unstable. So, the whole stability problem we break into this, that what is my this amplifier is unconditionally stable if and only if gamma in is less than 1 and gamma out, both of these should satisfy gamma out is less than 1 for all passive source, or I will say ZS and ZL. So, amplifier is unconditionally stable if for all passive, because generally we are talking of passive source and load impedances, but this amplifier should be unconditionally stable. Now, we have seen that these gamma in and gamma out values, they depends on S parameters of the device and also load and source conditions. So, we can find out this. So, we can find out some criteria, or we can find out on the Smith chart that whether this is taking place or not. Similarly, amplifier is potentially unstable if gamma in is greater than 1 or gamma out, here not and, because this was unconditionally stable, it is potential unstable if either this or this, gamma out is greater than 1 for some passive ZS ZL, not for all. Even if for one, then we will say it is potentially unstable. Now, we can make an amplifier conditionally stable. That means, though it is potentially unstable, we will avoid that combinations of ZS and ZL, and then say that if I avoid this set, these particular choices of ZS ZL, then I will say that it is conditionally stable if gamma in is less than 1 and again you see and gamma out is less than 1 for a certain range of passive ZS and ZL. So, this is important because first we will see whether we can find out whether it is unconditionally stable. If the network is unconditionally stable, that means whatever ZS, ZL I choose, still it is always stable, then no problem, I will go ahead, I will start concentrating my effort on designing the input and output matching networks, so that to achieve a particular gain or maximum gain or other things. But if it is not, if I say that no, there is a potential instability, then first I will have to determine what is the range of ZS and ZL that I can choose, so that the amplifier becomes in the stable region. So, based on this we can say that unconditional stability implies that gamma in magnitude, which we already have seen in earlier NPTEL classes, that it is S11 plus S12 S21 gamma L by 1 minus S22 gamma L, that should be less than 1, and gamma out is equal to S22 plus S12 S21 gamma S by 1 minus S11 gamma S, that also to be less than 1. Now, if we have, if the transistor is unilateral, which we already discussed that many practical transistors is unilateral, then these conditions become simplified, that gamma in becomes unilateral means S12 is 0. So, gamma 1 is S11 less than 1 and gamma out S22 less than 1. So, for a unilateral transistor I can always check, because manufacturer always gives me the S parameter, or I can measure the S parameter by modern devices, network analyzer, that we have already seen in earlier classes. So, and if I find that okay, the device is unilateral, its S12 is equal to 0, this means S12 is 0 or approximately 0, and then I see that S11 magnitude is less than 1, S22 magnitude is also less than 1, then I know that its input reflection coefficient, output reflection coefficient also will be less than 1. So, I will be happy, I will go on designing the actual thing. If it is not, then, or if I can also find that S11 is greater than 1 or S22 is greater than 1, then I will be worried and I will have to do some more thing. That some more thing is called the stability circle. I need to get a Smith chart and put some stability circles on that. So, that we will be doing in the next class, that we will be seeing that how when I have a potentially. So, in the next class we will be seeing that in potentially unstable cases, how to make conditionally stable amplifier. So, we need to demarcate some zone of ZL, ZS, etc., so that we won't touch that, and we will also demarcate the zone where we can choose ZL, ZS from. Those are called stability circle drawing and determining the region where it can have conditionally stable thing. So, this is something like whatever you have learnt in control circuit classes, that any network that when it is becoming unstable, you can find that conditionally how to make it stable. We will also see that in the next lecture.